Well, good afternoon. Thank you for sticking out the conference to hear one final talk. I'll do my best to keep things interesting and lively and hopefully inspiring on that. Networking in the data center. As the speed of innovation that is going on within the data center is just, frankly, truly amazing. I can't quite understand it. The big change that's going on right now in a data center is a transformation from what used to be a CPU-based architecture, which is predominantly a serial activity, to one of a GPU-based architecture where it's a massively parallel activity. And it's that transition that is driving an accelerant of both the adoption of next-generation data center technology, but of the technologies that are necessary to make it work in that. And you can think about this next generation as really it's the connectivity of everything to everything. And I say that because in the world of fiber optics, the world that I come from, it has been about point-to-point connectivities and as high capacity between those two point-to-point connectivities as possible. And when you connect everything to everything, that's not the case anymore. The case is about going from one node to every node with minimal latency, with maximum connectivity in that, as opposed to going through architectured switches. So the architecture shift that happens in this process is the shift to parallel processing via the GPUs, the adoption of GPUs. But it's also of the restructuring of the switching architecture, right? And so instead of having a multi-layered Klaus switching structure, in the large model sense, you need to strip that down to a single layer of switching architecture. And you do that for latency purposes, you do that for cost and for power purposes. But it requires now a greater, what they refer to as radix, a greater connectivity from each one of my GPUs to many, many other GPUs. And that. Massively parallel, low latency, low power drivers. What that ultimately limits you is in how much power you can get in the rack. How do you create that connectivity in there? And ultimately, it's been mentioned by a number of speakers in the past, as you drive that, you enter a realm where the data center, its primary limitation to its revenue, to its application, is the availability and the cost of power. And we'll get back to the significance of that in a minute. I throw this slide in here as a starter because this is kind of an extension of the plenary talk that was presented by Pradeep Sindhu, a friend of mine, but also a part of the CTO team at Microsoft, is presented at the OFC earlier this year. And I'll let you read through the words. I'm less concerned about that, but he establishes a couple of interesting hierarchies. He establishes the term, or the industry has established a term of what's called scale up, which is the localized high connectivity between GPUs. This single layer of switch that allows the most efficient communication and parallel processing for the data center. And then the second one is the scale out. The scale out is the more traditional CPU-based architecture where I have a multi-layered switching structure where I'm going to communicate through that multi-layer switching structure, which is over a greater latency, greater issues. It's more traditionally associated with transceivers that have high point-to-point connectivity, whereas that scale-up is not. It's measured by the capability of high multi-point to multi-point capability. Then ultimately you exit the building and you've got some type of inter-data center interconnect in the system. Each one of those tiers has a different order of magnitude of what I'll call transceivers, put into the big bundle of transceivers. In the scale-up market, you're going to see transceiver counts that are well into the hundreds of millions of units per year. That's in the scale-up market. In the scale-out market, you're going to see units that are in the millions, maybe up to 10 million units per year. So there's a solid order of magnitude, maybe even 2 orders of magnitude difference between the number of transceivers in the scale-up network than of the scale-out network. And then you're going to go down another order of magnitude of how much of that goes into between the building connectivity. And pointing all this out, what's clear, important to understand is that scale-up network, frankly, is today solved by just copper traces, right? And copper traces will no longer be able to satisfy that going forward. And if you look at this, I find this slide shocking. I find it first shocking to realize that present day racks of gear that are shipped out dissipate 130 to 150 kilowatts per rack. I think that's an amazing number. What is truly stunning in there is they contemplate 800 kilowatts per rack. 800 kilowatts per rack is just an astronomical number, at least from my senses of it. You know, data centers used to be 20 megawatts. You're talking about 20 racks being equivalent to a data center. And you can start understand that anything that has to do with power, consumption, or energy availability is the impediment to data centers, right? And it's important to understand that the economic driver of why they would want to do that is there, right? The data center guys, they'll go out, Microsoft goes out and buys, a defunct or a mildly defunct nuclear power plant, right? Because energy availability is justified in that expense because of the market opportunity that's coming from this. So the question is, how do you go about and how do you facilitate this? Are you really going to achieve 800 kilowatts per rack, or do you need a new technology to help alleviate that problem? Okay, breaking the part out, we've got two pieces of the network. There's a scale-up network, which is the low latency, high interconnectivity of GPUs, and there's a scale-out network, which is the connection of these GPU clusters to each other. I'm going to spend the entire time talking about the scale-up network, because that's the one that frankly doesn't exist today in normal transceivers, but is going to substantially outgrow any of the other sectors of the data center. Today, the largest implementation of that scale-up network sits in the form of a rack of NVIDIA gear. And I don't mean to position NVIDIA against everyone else, but it's a nice piece of gear to distinctly talk about what this dimensionality is. For today, in one rack of gear, they'll have 72 GPUs. Those GPUs talk to each other through a single layer of switching, and that single layer is actually, I think it's 9 switch cards in the system, and the longest trace length between one GPU and a switch is 1 meter. Each of those trace lengths either handles 100 or up to 224 gigabits per trace. Today, it's implemented via copper wire. It uses a single layer switch technology. Where do they want to be? Well, in 3 years, they need the architecture to expand from that 72 GPUs to 512 GPUs. And so now a single cluster will be 512 GPUs with the presumption that 512 GPUs don't fit within a single rack. Then they have to go to multiple racks. They have to go through the same single switch layer architecture in order to maintain the latency and the power efficiency. They'll probably stay in and around that 200 gigabits per trace lane. Possibly they'll upgrade that to 448. And out of a disruptive perspective, they may actually backtrack from there and go to a much more widely parallel interface. So I leave all of those are optionalities. I'm going to maintain that serial speeds will win in the end, and we'll see whether that holds true. All that comes together and says, well, how many GPUs are we talking about here? What do we really expect? Today, high-end GPUs, somewhere around 6 million units will go out this year, plus or minus. The Blackwell version, the Blackwell GB200 variant, I think is somewhere around 3 million units of that 6 million. But they expect by the time you get around 4 years from now to 2029, to have a total of about 70 million GPUs. 50 million of those GPUs are your high-end GPUs. They're the NVIDIA high-end. They are as Google and Microsoft and AWS bring on their equivalent parallel processing units, they add up to somewhere in the order of 50 million units. And those 50 million units, well, they translate into these transceivers. Basically, the transceivers are copper traces are going to get replaced by upwards, by 2029, upwards of 200 million units of transceivers. So the question is what are they? What are the optionalities? What technologies can you use to fuel that interest? Understanding I've simultaneously gone from 1 meter to 10 meters. When I go to 10 meters, I'm going to have a really hard time having copper deliver that data, so I need something different. But I'm filling a copper slot. And they're not going to put anything that's a heck of a lot more expensive or a heck of a lot more power into that slot because they're used to paying the price of a copper trace, right? And that's the challenge to the technology industry. How do you do that? Can it be done? And so you look at, okay, well, I can do copper, I can do silicon photonics, maybe I can do widely parallel LEDs or maybe widely parallel VCSELs, what it will bring up in a minute, another radio alternative on that. And you see copper's lovely, it's reliable, it's low power, doesn't, it's copper. It doesn't, its cost, actually, frankly, I find it's more expensive than I thought it was, but it's still a lot cheaper than optics. It's got scale. The only problem is it doesn't go far enough. And so you're going to go from your 72 GPUs to your 512 GPUs, and all of a sudden you can't do it in copper, but you're used to paying the power and the dollars price of copper. Silicon photonics, yep, they can do the reach, but they are inferior in every one of the other categories. And probably the biggest and most important category is reliability. Right? They will not put anything that compromises the reliability of their high-end GPU or their high-end switch. The cost of that reliability risk is too great. And understand, because you are parallel processing information, the error rate requirement just went up, right? What used to be an acceptable error rate, because I've got so many parallel simultaneous structures going on, it is no longer sufficient to operate at the same error rate that you operated in the past. So reliability actually is, the need for reliability has gotten harder. So what's the alternative? And this is the formation of our understanding of how AttoTude thinks about the problem. And the alternative is to go back to the simple thought to, what is communication? Communication in my world breaks into two pieces. I've spent 40 years of my career on the photonics side, and of photonic integration. I solved all sorts of very cool and interesting stuff with photonics. At its basics, it takes a band of information that someone finds useful. I move it, I up-convert it to a frequency. In the case of 1.5 micron light, I'm up-converting it to 193 terahertz. And I do that because the transmission media that I use, silica fiber, has a minimum loss at that level, right? And it's the same communication process that I would use in all my radios. I'd have a band of information, I'd uplift it to some frequency that my transmission media works at, whether it's an FM radio, a wireless transceiver, or something that sits in silicon. In the photonics world, they love the fiber. The fiber is unbelievable, right? It's high volume, it's low cost, it's high reliability, it weighs almost nothing, right? If I put data in one end, I'm going to get it out in the other end, and the losses of that transmission media are just phenomenal. The problem with that technology is the need for photonics. And this is slightly painful for me of 40 years of my career developing photonics, but the reality is photonics, they cost money, they have a difficult reliability aspect to it. Their degradation processes are associated with recombination, not with change in resistances. As a result, they have more reliability-related issues associated with the free carrier recombination inside of a laser. And so you want to take the user experience of a fiber, a low-loss transmission media, which is flexible, lightweight, and reliable, but I need to take advantage of the radio. So now the question is, my thought process in this was, the fiber world went on and they started developing hollow core silica fiber. Microsoft buys an outfit out of Southampton, and they start developing a hollow core fiber. They bought it primarily for the lower latency, because the index of refraction of 1 of air gets the information either further or faster to its destination than the index of refraction of 1.5. But then once you realize, hey, I got a hollow core, I no longer have to be at 1.5 microns. What wavelength do I want to be at? And there's lots of ways of answering that question. There's one way it says, well, and Microsoft leans in this, said, well, I don't like the losses, the energy state of a 1.5 micron photon. I'd rather be at 1 micron, a little bit higher energy, a little bit more efficient transfer, less recombinatory losses, et cetera. But I look at it and I say, I would like to be at a wavelength that I can make with transistors, right? And then I start saying, I want the fastest transistors I can get my hands on to get to the wavelength that can fit in something that looks and feels like a fiber. And that's where terahertz comes in. 1 terahertz in air has a wavelength of 300 microns. 300 microns is now in the realm where I can get into a piece of transmission media that is light, reproducible, flexible, and as it turns out, can be sufficiently low loss for the applications of data centers. And now I can take the user experience of a fiber, but the reliability, cost structure, scale capabilities, power capabilities of radios, of electronic radios from that. And so the direction, and we believe the future, is to be able to make fiber-coupled terahertz radios. What's that allow you to do? One of the key considerations of next-generation architectures, and we'll talk a little bit about why, is you'd like to be able to move this transceiver from what is currently on the bulkhead of their card integrated into next to their, what I call their high-value ASIC, whatever that would be, the switch chip or the GPU, et cetera. You'd like to get that transceiver in there. The reason why you like to get that transceiver in there is the traversing from the host to the back of the chassis or the front of the chassis actually turns out to be a really horrible link. And it's a link that's dominated by sending information over a copper wire, sending baseband information over a copper wire. And that causes a lot of headaches, and in the end, those headaches cost you a significant amount of power. So the ideal is if you can take that terahertz radio, the preferred embodiment would be actually integrated right next to the chip or integrated into the SerDes function within that chip. And matter of fact, I postulate that what you really want to try to do is you want to change the SerDes from a PAM4 SerDes, and you can either leave it as a PAM4, but once you're there, you might as well change it to a QAM4 SerDes, right? And if you make a QAM4 SerDes, then voila, you get a lot of extra reach. And the incremental power difference between those two actually turns out to be relatively small. Let's look at a few structures and compare them. Today, scale up, and I'm going to, again, stick into scale up, not worried about scale out. Scale up, 10 meters. 10 meters gets the world pretty excited on the scale up world. Today, they've got my host chip, they have an I/O element in some form or another that consists of a DSP and a SerDes. They launch PAM4 onto a copper cable, whether it's in the form of a twin-ax or some other trace. And you can go, realistically, it's about a meter, meter and a half, but I'm going to give them 2 meters. Reliability, cost, power are great. Reach is insufficient for next generation scale up. And scale, because of that, also doesn't work so well. So the first option is, well, I'm just going to go through a pluggable optic at my chassis. I'm going to leave my host, I'm going to leave my DSP and my SerDes the same. I'm going to go send that baseband information to the back of my board. In that process, I'm still going to consume a lot of loss, a lot of reflections in that process that my DSP has to correct. And because of that, I'm going to end up having a DSP retimer at that element. And all of a sudden, I got 2 DSP engines where you should have 1. And so I've thrown a pile of power at that. That's not going to work to scale up this capability. I can throw in an optical silicon photonic based transceiver at that point, and hey, I got my reach. but I don't have my power, and I certainly don't have my cost. I can move that silicon photonics back in, and if I get that optical layers close enough to my host party where I'm no longer a 20 to 40 dB link, but I got a 5 dB link going from chip to chip, well, that's pretty good, and that gets me the 10 meters that I need. It's more power than I like, and the reliability and the cost structure are definitely things I don't like, because my metric is how do I measure to copper? Well, silicon photonics measure to copper doesn't do so well. And so this is where the opportunity is to take what we talked about before and say, well, great, we're going to move a piece of electronics, and that transceiver, that terahertz transceiver, which is built from transistors, which is used to living in the existence, the environment of transistors, we can move that in there. So I'll take that 5 dB link budget from this DSP and SerDes, connect to the terahertz transceiver, and I can go 10 meters. And I meet all these requirements. I'm going to give myself, it's slightly more power than copper, but it does actually do very well when you get into the reliability, the cost, and meeting the reach and scale. Finally, if you put yourself as a system designer in there, you're going to want to take that DSP SerDes, and you're going to say, why do I have that at my host station? DSPs and SerDes are really events that should sit at the transceiver. And so those two elements, that terahertz transceiver and DSP SerDes, should logically sit in the same spot so that the DSP can be designed to maximize the value of that transceiver. And actually, when you do that, what you'll find is it's not 10 meters, you can go up to 100 meters in that process. And so that really lays out that the terahertz has a really beautiful vision of where the system architecture can go, and it utilizes technologies that inherently meet their criteria and scale with their criteria. So where are we? We're in the early stages and validating. We've validated the raw technologies. We've validated we can make indeed terahertz transmission. And the biggest, what's shown here in the top left is the characteristics of terahertz amplifiers. Those amplifiers meet the criteria, and if you can make an amplifier that has a decent noise figure, power, gain, et cetera, well, you can kind of pull together the rest in that process. It's made from technologies that is manufacturable, and a matter of fact, is actually very reliable from that. We've demonstrated that over 5 meters, depends on who I'm talking to. I'll either call it a fiber or I'll call it a wire, but over a transmission media, which is moderately low loss at terahertz. We're in the process of further evaluating that to extend it from 5 meters up to 10, 20, and 40 meters in that process. What's shown here on the right side is this is a QAM modulation format that we've extended through those transceivers. Take a step back and now compare the silicon photonics versus the terahertz transceivers. To think about it in a very simplistic form and logical form, remember you're taking a baseband information. That baseband processor, the first order, is the same between either of them. I'm defining my modulation format, preparing my data to be sent over something, and then I got to mix it either with a 193 terahertz laser oscillator, or I'm going to mix it with a 1 terahertz oscillator derived from VCO and or amplifiers in that. Broad statements here, so bear with the inaccuracy of generalized statements. Lasers dissipate watts to achieve that as their local oscillator. Transistor circuitry, you're going to dissipate hundreds of milliwatts to achieve the same LO capability. And that starts envisioning where the power leverage is for that. Optical modulators take volts, right? The electro-optic coefficient to modulate an optical signal takes volts. As a matter of fact, this is one of the key challenging issues of silicon photonics, or maybe the use of lithium niobate, thin film lithium niobate on silicon photonics. I still need volts. To modulate the electronic mixer, I'm sub-volt, hundreds of millivolts as far as signals that I need to supply to that element. So the basic architecture of a transistor-based element as opposed to a recombination-based optical element inherently gives you some tools, doesn't guarantee it, but it gives you the tools in order to address power and that. So if you compare the silicon photonics to the terahertz, one is they use lasers. They do put the lasers in a different location, but they still have to pay for those lasers and the unique packaging of those lasers. The lasers and the optics define the reliability, and those reliability statistics are defined by recombination, carrier recombination within a semiconductor, whereas on the terahertz side, it has to do with the degradation of gain associated with any change in resistances or parasitics that go in that process. Two very different processes. A 1 micron beam of light, when you're packaging it, needs to be held to a 10th micron mechanical tolerance. And that, therefore, the packaging needs to accommodate the fact that I got a very small beam of light. If I've got a 300 micron E&M wave and I have to match my couplers and my fibers to that, well then I'm in the tens of microns positional tolerances. It's two very different packaging cost and packaging complexity ends. Latency, depending on how you go about doing it, as we talked about earlier, you may be sending this in over confined free space, in which case then you buy speed or your latency within the system. Power, in the end, power is important, but the power on both of them are low enough where it is not the deciding factor. The deciding factor in the choice of technology, the number one, is reliability. That'll be the driver. Cost structures, I will put my bets on people that are used to making ASICs to be able to achieve the cost structures in their manufacturing process over the ones that stem it out. And really, the cost structure is better shown by the bill of materials for a silicon photonics transceiver at the co-packaged location has 43 elements to it. 43 discrete elements that have to be made, assembled, tested, et cetera. Bill of materials for a terahertz transceiver is 8 elements, and it's dominated by the ASIC itself. In the end, why terahertz? Why do I think this will be a significant benefit to the field? It's ASIC-based. There is existing manufacturing infrastructure. The transmission media can be designed and made in a high volume capability. Reliability, I'll kind of skip the next, simplified packaging and that. And how that impacts, I'll say thank you and comment on, it is the impetus of the AI-structured or highly parallelized data center infrastructure, which is going to create this new market for active transceivers called scale-up, and the connectivity of everything to everything that is going to enable that technology or demand that technology transition. And I think the wired terahertz transceivers have a good shot and a good opportunity to exist there. So with that, I'm going to wrap it up, and I think we have probably about 5 minutes for questions if anyone has any questions. Okay. And if you're in the wings, I don't have a prayer of seeing you. Any questions? Yeah.
Okay. At about 1 terahertz range, I see still actually dielectric loss could dominate your overall actually transmission loss. So in one of your slides is saying that your solution can cover 100 meters. What kind of channel that you are trying to build to actually overcome these losses?
Yeah, so I'll answer in 2 phases. The transmission media, we believe a good design target is about 0.5 dB per meter. And 0.5 dB per meter, you can get 20 meters, 10 dB gets you 20 meters, and that. And we've worked through, and those demonstrations exist. As I indicated before, as you continue to advance that loss, I actually think there's another order of magnitude that can be had in that, but I will purposely, honestly admit we have not achieved that next generation of technology. But I do believe, like in all new technologies, there's a lot of good reason to believe that you can get out to about 100 meters. Initial target markets, initial target utilization is all about the scale-up market and all about get the market at the 10 to 20 meter application space first. Okay.
You mentioned the transceiver ASIC, and then you showed a 25 dB gain or so, 11 dB noise figure, right around a terahertz.
Yep.
So would one interpret that to be a highly integrated technology like CMOS or some other silicon process, or does it involve, indium phosphide or something like that?
So we haven't gone in and disclosed the particular node or the particular technology, but very comfortable that the technology has proven itself in high volume manufacturing to that. So you guys are better at, frankly, what's the state of the art of different technologies out there. The ones that we've worked on and developed and advanced, we haven't disclosed how we get there.
Got it,
Okay.
thanks.
I think you mentioned silicon photonics, terahertz, and parallel using micro LEDs. And I think you didn't get back to that. I was just wondering where you kind of look at that versus terahertz, because you have LEDs in your TVs and they're pretty mature technology. I was just curious what your thoughts there.
Yeah, so there are two driving philosophies, and there is a thrust, and I purposely mentioned it on there, of moving from a serial stream, 224 PAM4 serial stream, to maybe a UCI type of format based to drive a set of parallel optics, specifically an LED array, potentially as maybe a VCSEL array in that process. The LED arrays are actually very interesting from an incremental power perspective, because you're driving these LEDs at very low speeds, but you have to ironically move from that UCI interface. You actually have to further parallelize that signal. You can't get out, so the LEDs are running at 4 or 5 gigahertz clock cycles or so. You're not getting off your host chip at that speed, because the bump bonds, you just can't afford that many bump bonds, right? And you think about the switch. Well, the switch is going to migrate from it's already getting to 100 terabits. It's going to get to a petabit, right? How does a petabit get a petabit of information off? It's going to have to serialize it to some level, right? And so now the question is, as I look at my roadmap from that switch architecture, I can't sit there and stay at 5 gigahertz. And let's say the LEDs get better, 10 gigahertz, 20 gigahertz. I can't stay at that level because it inhibits my ability to drive things to a petabit. So the LEDs, that's their burden. And I mean this sincerely. You put a pile of engineers around with the tools, and that tool set works with LEDs, they will solve that problem. And then the question is, did they do it fast enough, cheap enough, and with enough legs to go forward? And I've got some very close friends that are involved in that architecture, and I applaud the incredible technologies they've developed, but they have a different set of problems. What was interesting, if you go back to the OFC talk by Pradeep, he says, you know what? Give me 200 gigabits per lane, and we can stay at 200 gigabits per lane, because in an everything connected to everything architecture, you don't actually want to go faster and faster speeds. You want to maintain 200 gigabits in this radix. What you're going to want to do is have many, many more aggregate capacity of that 200 gigabit going forward. And I think they're going to stay in that serial level for that. So that's kind of where I'm placing my bets. I think I had, okay, so should we wrap up? There, great. Thank you guys very much. Appreciate it.